Section 9.3. Again, we're doing hypothesis tests for a one population mean. We looked at how to do a hypothesis test using the critical value approach. In this section, we're going to look at what we call the p-value approach. This is another way we can do this hypothesis testing. So when we did the critical value approach, we found out a cutoff value, and then we compared our test statistic to this cutoff value to determine should we reject the null hypothesis or we don't have enough evidence to reject it. For the p-value approach, we're going to start off, say, assume the null hypothesis is correct, and then find what is the probability that my test statistic is close enough to meet the significance level. So let's kind of see what we mean. This is kind of vague at this point. So we're going to go back to that same data we used in section 2, Kevin and Diego. So average drive of the golf ball is 275 yards. Kevin is trying to prove this by doing a sample. So he samples hitting 25 drives with the following data, and he had another typo here. The sample mean is 264.4 yards. And he's trying to say, hey, that's good enough. So far, it's the same problem. We're going to stick with the 5% significance level. We need to do our hypothesis testing, so we need the null and the alternate hypothesis. So my null hypothesis is still going to be mu equals 275. My alternate hypothesis is going to be mu is less than 275. We are still the same. We're going nothing different between a p-value approach, a critical value approach. We're assuming normally distributed. So we get our mu sub x bar and sigma sub x bar. Again, our test statistic is still going to be the z-score of the sample mean. So again, everything up to this point is exactly the same, no matter which approach we use. Now, with the p-value approach, we're going to say what's the probability that that test statistic is good enough? What's the probability that it's going to be worse than, say, that we're saying if 264.4 yards is close enough to the mean, what's the probability that it's farther away? What's the probability that the value would be less than that? That's kind of what we're looking for. So we're going to start and say, what's our test statistic? What's the z-value? The z-value is our negative 2.65. So we look at the normal distribution and say, what's the probability that that distance is going to be at most have a z-score of negative 2.65. So probability that z is less than or equal to negative 2.65 is 0.004. And this is much smaller than the 5% significance level. So we are going to reject h sub 0. We're saying if this is the best we can do, there's less than 5% of the scores of the drives that will be that much or less. So that does not fit that 5% significance. So we are going to reject the null hypothesis. So again, the p-value of a hypothesis test, that's the probability of getting sample data at least as inconsistent with the null hypothesis as the sample data actually obtained. So we're saying, this p-value is what's the probability that we're at least that far away from the mean. That far or farther from the mean. We're going to use that p to represent the p-value. Again, the smaller p is, the closer p is to 0, the stronger the evidence is against the null hypothesis. That means if a really small value of p says that, almost nothing is going to be that far away from the mean. So that's not very close to the mean. That's about as far away as you can get. So that's one thing. This p-value gives this idea of how strongly, how strong is the evidence against the null hypothesis. That's one value of looking at this p-value. It's more than we're saying, I reject it. It's kind of like, I strongly reject this with these small values. So, I went too far there. One of the nice things with the p-value, with the critical value test, we had to say, okay, find the cutoff value, then look at my test statistic, and then I have to figure, well, in some case I want it to be less than, and sometimes I want it to be greater than. With the p-value, we will always use these inequalities. If the p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value is greater than alpha, we do not reject the null hypothesis. So the p-value is the observed significance level. So what we observe as compared to what is specified. What significance level are we conducting the test at? What significant value do we observe? And if the observed value is less than the tested value, we're going to reject it. So we got to be careful when we determine these p-values. Because if we always want that inequality to hold the same way, we have to take care of the left-right, double-tailed, two-tailed, and take that into account when determining the p-value. Again, we're going to assume null is true. What's the probability? It's that the test statistic is extreme or more extreme than what we see, or far from what we would expect. So let's kind of work through these and look through a few examples here. The one we did was with Kevin and Diego was left-tailed. Those are the ones that are most straightforward. So we're going to say here my test statistic is negative 1.19. So we need to find the p-value of my test statistic and compare it to the 5% significance level. So since it's left-tailed, we can just look it up on a table. Look at z is negative 1.19. We're going to get a p-value of 0.1170. 11.7% is to the left of negative 1.19. So we're a 5% significance level. So 0.1170 is greater than 0.05. So that means we will not, there is not enough evidence provided to reject H sub 0 in favor of H sub A. So basically we're over in this area here. Here's our negative 1.19. This would be where our p-value is. And this is 11% of the data. And I'm looking at 5% significance, so that's going to be somewhere over here. So we're more than enough. We're more than close enough. If we're doing a right-tailed test, and this one we're going to have a z-value of 2.85. Notice this is a positive z-value. If it's a right-tailed, your z-value should be positive. Because if you're doing a right-tailed test, you're trying to prove that the mean is greater than the null, the mu sub 0, and your test statistic is going to be something that's less than it. It's obviously not going to work, right? So think about that. Look at some common sense things. Z is 2.85. We look that up on the table, we get 0.9978. That's the values of Z is less than 2.85. We're right-tailed. So we want to be to the right or greater than 2.85, so we need the complement. So for a right-tailed test, the p-value is going to be the complement of this. So that's 0.0022. Our 1% significance level is 0.01, and if we look at this, we're going to say 0.022 is less than 0.01. So that means the data does provide sufficient evidence to reject H sub 0 in favor of H sub A. There's only a 0.2% chance that we're this close. And we need to have at least a 1% chance. So it fails. And we reject H sub 0 in favor of H sub A. For a two-tailed test, so again here we're going to give a negative z-value again. With a two-tailed test you could be negative or positive because we're on either side. So again we're going to start with looking it up on the t-test, or on the t-test. We're going to look it up on the normal distribution. We get a 0.0436, but this gives me the left tail. I need two tails. So but I know that it's normal, so it's symmetrical, so I'm going to double this value. My p-value is going to be twice this, so I take 2 times 0.0436 to get 0.0872. Because I'm a two-tailed test, I have to consider both sides. The area on both sides of both tails have to add up. So at 5% significance, we're going to say that the p-value is bigger than alpha, so we do not have enough evidence to reject H sub 0 in favor of H sub A. So if you notice on the p-test, we adjust the p-value so it makes sense so that we can always use the same inequality, p greater than alpha. Versus with the critical value, we're going to, in each case, we have to say, here's my critical value. Now what do I have to think about my test statistic as compared to that? So two ways to do it. It's pretty much the same. If you look at the steps, we need a normal population or a large sample. We need to know sigma. That's the same. State the null and alternative hypothesis. Yep. State the rejection rule. So we're going to have to find, okay, we calculate the test statistic and use this to find the p-value. And then we're going to compare this p-value to whatever is my significance level of the test to reject or not reject the null hypothesis, and then we interpret this. It's just another way to do this. You should get the same result in terms of did I reject or did I not reject the null hypothesis, no matter which way you go with it. It kind of depends on how you like doing it. So let's give this some try.